All right, let's get right into it. We're going to travel back in time to 1963 to unpack this amazing story about a meteorologist, a very early computer, and a tiny, tiny rounding error that accidentally gave birth to an entire new field of science.
So everything really kicks off with this simple but, incredibly frustrating question. It's something that bugged scientists for decades. We know for a fact the atmosphere follows the laws of physics. Things like gravity, thermodynamics, fluid dynamics, all that good stuff. So if the rules are fixed, why on earth can't we predict the weather more than a few days out? It feels like we should be able to, right?
And this is the very heart of what scientists started calling the predictability puzzle. It was this frustrating clash between what the theory said should be possible and what was actually happening in reality. Now, to really get a handle on this puzzle, you have to understand this one key idea: a deterministic system. Think of it like a perfect long chain of dominoes. If you know exactly how that first one is pushed, the angle, the force, everything, you can, in theory, predict how the whole chain is going to fall at any point in the future. And for a long time, the atmosphere was basically assumed to be just like that. Okay, so this brings us to our main character, Edward Lorenz, and his really clever way of tackling this massive problem by thinking small. So Lorenz is a meteorologist over at MIT, and he's just fascinated by this whole puzzle. He knew that trying to model the entire planet's atmosphere it was impossible with the computers they had back then. So he decided, you know what, I'm going to create a miniature version, a kind of toy weather system that I can actually study. And just to give you a sense of the challenge he was up against, these are some of the real equations for atmospheric convection. I mean, look at them. They are a tangled mess. Trying to solve these for the whole planet was, and honestly still is, a monumental task. But this is where Lorenz's genius really shines through. He managed to distill all of that insane complexity down to just these three elegant-looking equations. They described a much simpler system, kind of like the air currents over a pot of water being heated, but it was simple enough for his computer to handle while still capturing that essential, chaotic behavior of real weather. So, with his toy weather chugging away on his computer, Lorenz was about to stumble onto something that would change science forever. And the best part? It was completely by accident.
So you gotta picture this. Lorenz is running one of his long simulations. He wants to get a closer look at a section that he found pretty interesting, so he decides to just restart it from the middle. To do that, he looks at a paper printout of the data, finds the right spot, and then manually types the numbers for those conditions back into the computer. Just a simple, everyday, time-saving shortcut.
But here's the crucial, tiny detail. The computer, in its memory, was storing the numbers out to 6 decimal places. His printout, though, just to save paper and space, only showed 3. So he typed in 0.506 instead of 0.506127. I mean, it's an absolutely infinitesimal difference, less than 1 part in 1,000. It seemed completely, totally insignificant.
So he sets the new simulation running and walks away to get a cup of coffee. When he comes back an hour later, he is absolutely stunned. The two paths, which should have been basically identical, had started to wander apart. And soon, the new simulation was on a completely different trajectory. That tiny, tiny rounding error hadn't just nudged the result a little bit, it had created a totally different future. This was the moment, the big revelation. In the very dry, technical language of his 1963 paper, he just noted that two states that differed by imperceptible amounts could evolve into considerably different states. He realized right then and there that if his super simple, deterministic system behaved this way, the real atmosphere must too. But this wasn't just about things being unpredictable. When Lorenz plotted the data from his equations over a long time, something else emerged, something beautiful and totally, totally unexpected. And this is it. This is the shape that appeared. Today, we call it the Lorenz attractor. It kind of looks like a butterfly, or maybe a strange, twisted figure 8. This is the visual map of his system's behavior. And what's so wild about this is that the system never leaves this shape, but it also never repeats the exact same path twice. It was this perfect mix of order and total unpredictability. It was deterministic, right? It was following his 3 simple rules, but its output was forever creative, forever new. He had a name for it: Deterministic Nonperiodic Flow. This weird shape had some really mind-bending properties. So think of it like a roller coaster that always stays inside the amusement park, but the track is constantly, infinitely rearranging itself so you never, ever take the same ride twice.
The path is bounded, it stays inside that butterfly shape. It's non-periodic, it never repeats. It orbits those two center points, but it randomly switches between them, forever exploring a new path inside this beautiful, contained space.
So, okay, how does this beautiful shape explain why weather forecasting is so darn hard? Well, let's connect those dots.
This is the formal scientific principle that Lorenz had just uncovered: sensitive dependence on initial conditions. It's a fancy way of saying that for complex systems like the weather, tiny, immeasurable differences at the starting line can get blown up over time, leading to massively different outcomes down the road. And this big idea was later given a much more poetic name: the butterfly effect. You've heard the question, right? Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Well, Lorenz's work showed that, yeah, in a manner of speaking, it actually could. The fact that it's impossible to measure the starting state of the atmosphere with perfect accuracy, to know where every single butterfly is, that's what makes long-range prediction fundamentally impossible.
And Lorenz knew it right away. This quote from the abstract of his paper is just a masterclass in scientific understatement. He wasn't just examining it. His results had pretty much just proven that the dream of perfect long-range weather forecasting was probably just that, a dream.
But the impact of Lorenz's accidental discovery didn't stop with the weather. Oh no, it was about to ripple out across all of science. That 1963 paper basically fired the starting gun for chaos theory. All of a sudden, scientists started seeing this sensitive dependence everywhere, not just in the weather, but in the unpredictable swings of the stock market, the complex rhythms of a human heart, even the orbits of planets in the solar system. A whole new science was born from that one rounding error. And so that's where we'll end it. What Lorenz showed us is a universe that is, at the same time, completely orderly and completely unpredictable. It's a world where the rules are fixed, but the future stays forever a mystery. And it really forces us to ask, what other parts of our lives, our world, are governed by this beautiful, strange, and ultimately humbling chaos?